Dipende, io aspettavo no, devi visualizzare la tabella dietro. No, adesso. Ok. Okay. Good afternoon, everybody. We start with the afternoon session. And the first speaker is Maria Rosa Mazza from University of Innsbruck. And she will talk us about B-spline collocation matrices for Riemann-Liouville or Kabuto fractional operator, with a focus on the spectral properties.
Thank you, Fabio, for your introduction. Good afternoon, everybody. The results I'm going to talk about are contained in two papers that I have authored, one of which in collaboration with Matteo Donatelli, Carla Manni, and Hendrik Spiniers that are all here. And these results concern the spectral properties of the matrices that are obtained after B-spline collocation discretization of the Ritz fractional operator, with an extra eye to what happens if we switch from the Riemann-Liouville to the Kabuto definition for the fractional derivatives. Okay. Of course, I don't need to introduce the fractional diffusion equations to this audience. What I wanted to do with this slide was just to put on the table what is the model problem we started from, which is this space FD, where the differential operator is the Ritz operator of order alpha that ranges from 1 to 2, which is defined as the sum of the left-handed and right-handed fractional derivatives. Despite its simplicity, this model is commonly considered as a starting point for studying more involved models. So that's why we started from here. And because of the non-locality of this operator, concerning the boundary conditions, we go for the so-called absorbing boundary conditions, which means imposing that the solution is zero at the boundary, but also outside it. Okay. We all know that there are many definitions for fractional derivatives and that these definitions in principle are not equivalent unless the solution is smooth enough. One of the most famous definitions is the Riemann-Liouville one, is here. And this kind of definition is usually preferred for space problems, since it's not asking that much regularity in the solution. When the derivative that we have here in front of the integral comes inside the integral, then we talk about Kabuto derivatives. And this kind of definition is typically preferred for for time problems. That's because usually the solution is more regular in time than in space in the applications. And of course, this kind of definition is asking more regularity in the solution than the previous one. As I said, these two definitions are not equivalent, but we know there is a relation between the two, which is expressed by this formula here. And so this formula says that the Riemann-Liouville derivative is equal to a Kabuto one plus something else. And this something else depends on the solution and its derivative at the endpoints for the 1D case. And the derivative up to, say, the floor function of the fractional derivative. In case we go for homogeneous conditions, that is, we assume these conditions here, then actually Riemann-Liouville and Kabuto definitions are the same definition. Okay, as I said at the very beginning, our interest is to see what happens to the fractional derivatives and to the Ritz operator when we go for a B-spline collocation discretization. This means that we need to introduce two objects, the approximation space and the collocation points. About the approximation space, we go for the B-splines of degree p greater than or equal to 2 that vanish at the boundary. This way, the boundary conditions are automatically satisfied. So this S and P, where elements are the span of this set here, the B-splines from the node sequence that has P plus 1 nodes equal to 0, P plus 1 nodes equal to 1, and the rest that is equispaced in Z1. About the collocation points, a typical choice is to go for the Grevilla shift that are defined from the node sequence in this way. Well, let's have a look at how these two objects look like for a specific choice. In this case, n equal to 10 and p equal to 3. In this picture here, I'm representing by vertical lines, this colored ones, the node sequence, and by the blue dots, this here, the Grevilla system. First, we can observe that in the internal part of the interval, these two sets coincide. And also the other thing that we should observe here, speaking of the B-spline space, is that these internal splines, these green ones, are all a copy, say, of a same function, the so-called cardinal B-spline. Of course, here I'm also plotting these red ones at the beginning and at the end, which are not in our space. They don't even satisfy the boundary conditions. Okay, so collocating by B-spline means that we want to approximate the solution mu in our space as a P, then write it this form, and then compute the uj by imposing the collocation conditions in this way. This gives us a linear system whose coefficient matrix will have this form here. That's a sum of two matrices, left and right one, that corresponds, of course, to the left-handed and right-handed fractional derivatives, and the elements, as expected from the collocation method, are the evaluations of the fractional derivatives of the B-splines at the collocation points. Okay, now let's try to uncover the structure behind this matrix. We'd like to know if there is a structure in order to then exploit this information to know more about the spectrum. Let's fix first the attention on the left matrix. Well, I said that the internal B-splines are all a copy of our same function, the cardinal B-spline, and that the grid points are equispaced in the internal part of the interval. This means that we expect for the central part of the matrix to have a tablet structure, something that was already introduced this morning by John Pearson. So, for instance, in this specific choice of the parameters, what we expect is that what is inside this magenta square is such that these diagonals here are all made of a number, the same number that's repeating on the diagonals. About the corners, since they refer to the, let's call them external B-splines, but not in the internal B-splines, and since this corners corresponds only to a few row and column whose number varies with p, the degree of the splines, we expect that the corners correspond to a rank correction. So at the end of the day, we can write this left matrix as a sum of a tablets part plus a rank correction. The result is non-symmetric, as we can see, for instance, from this choice of the parameters here. And already, actually, the tablets part is non-symmetric. If we do the same reasoning also for the right matrix, we can, at the end, write our coefficient matrix as a sum of a tablets, again, plus the rank correction. And still, the result is non-symmetric, but now the tablets part is symmetric. Okay, to this point, I haven't specified whether we are going for Riemann-Liouville or Kabuto definitions, formulation for the fractional derivatives. So let's see what happens to the structure if we go for one or the other. Let's quickly recall the relation that I showed before for the case we are interested in, alpha that ranges from 1 to 2. We see that a Riemann-Liouville is equal to a Kabuto plus these two other terms. And then if we apply this relation to our basis functions, the B-splines, At the end, we have that basically these two definitions are the same definition up to the first and the last basis functions, the ones that correspond to index 2 and the index n plus p minus 1. This is because these two b-splines here have a derivative at 0 and 1 respectively that is not 0. And so in terms of matrices, doing this switch to Kabuto from Riemann or vice versa gives us some matrices that differ only by a column, the first column or the last column. And in other terms, we can say that the Riemann matrices differ from a Kabuto one by a rank 1 correction. If we're talking of the Ritz operator, then they will differ by, of course, a rank 2 correction. Okay, so now we know what's the structure of our matrix. It's a Teplitz class correction, and we'd like to use this information to know more about its spectrum. In this view, we need to say a bit more about the Teplitz matrices, especially the ones that are associated to Lebesgue integrable function, say f, that is the matrices that are built in this way from the Fourier coefficients of the function f. Well, what happens for this kind of matrices is that if f is non-negative, then if we take a sampling of f on its domain, which is minus pi pi, then we get an estimate for either the eigenvalues or the singular values. And in this case, in the literature, f is called the symbol, not only of a single Teplitz, actually of the Boole sequence of Teplitzes, because this result is true as far as n is large enough. For instance, if we take f equal to 2 minus 2 cosine of theta to the square, we can compare a sampling of this function, here actually 0 pi, just because the function is even, with the true eigenvalues of the Teplitz Tn of f, and you see that there is already a good matching between these two objects when n is just equal to 10. Okay, so what happens if we take a Teplitz plus something else? Well, it depends on what are the properties of this something else. But if we're adding to a Teplitz a correction whose trace norm is growing less faster than the square root of n, then the distribution result still holds in the eigenvalue sense. And moreover, if we add to a Teplitz a correction that is a rank correction, this time whose rank is growing less faster than n, then the central distribution holds in the singular sense. Okay, we need all this information to get information on our problem. Recall that the coefficient matrix is this one, a Teplitz plus a correction. The game is determine the symbol for the Teplitz part and then see if what we are adding is actually satisfying the properties that I have just mentioned. So we actually computed the symbol for the Teplitz part, and that it's this real values positive function. And you see there is a good matching between a sampling of this function Fp alpha and the true eigenvalues of the Teplitz part that is in our coefficient matrix. Moreover, we were able to prove that the correction we're adding to the Teplitz part is satisfying this condition. And then we, what we can say from the theory is that then this function is still giving information on the Boole matrix, not only the Teplitz part. This independently of the choice of the formulation for the derivatives, Riemann, or Kabuto. And note that here there are few outliers, and the number of these outliers is just depending on p and not on n. And the other thing that I would like you to observe is that in the Kabuto case, we still have these outliers, but these larger outliers have a magnitude that is greater than the one for the Riemann formulation. This same behavior in the same scenario is also replicated for the singular values, where again, since the correction is also a rank correction, we have that in both cases, Riemann-Liouville and Kabuto, there is a good matching between the evaluation of the symbol and the true singular values. And again, there are outliers. And again, in case of Kabuto matrices, the outliers are greater. The larger outliers here are greater than in the case of the Riemann-Liouville. And their magnitude is also increasing with n, as proved by these two pictures here, where n is equal to 80 and then n is equal to 160. Okay, so what's now the aim? We know the symbol. We'd like to know what are the properties of the symbol to see what this means for our matrix. Since I'm saying the symbol gives information on the spectrum. So if we study the symbol, we can have more insights on the spectrum of our matrices. And this is actually what we did here. These three pictures are representing the symbol, increasing p and varying alpha, and they clearly show the properties that we have proven analytically. That is that the symbol has a 0 at the origin, whose order is alpha. That the symbol has a decay at pi, and that this decay is going faster for alpha that tends to 1. And finally, that the symbol can be bounded in the proximity of pi by the symbol with alpha equal to 0, which is simply a polynomial, a positive polynomial that is separated from 0. Well, these first two properties tell us something about the conditioning of our matrices. They say that the matrix is conditioned in the low frequencies and in the high frequencies, with a deterioration in this case that is driven by both p and alpha. And the third condition says that we can isolate what is the source of the conditioning in the high frequencies that is due to p. Okay. So till this point, I'm saying that whether we go for Kabuto or Riemann-Liouville, the symbol is always the same. But on the other hand, we have observed that in case of Kabuto matrices, there are larger outliers. So with this in mind, we checked the spectral norm of the Kabuto matrices by providing some bounds for both one norm and infinitive norm. And what we showed was that in case of Riemann-Liouville, all these norms are always bounded by a constant. And it is confirmed in this picture here by logarithmic scale plot, where the Riemann-Liouville norm are the dashed lines, and you see they are all constants at the bottom of this picture. While in the Kabuto case, the one norm and then the spectral norm are both bounded by a term that depends both on n and alpha. And this is again clear from this picture here, where I'm also representing the norm of the difference between these matrices by this process. And then this picture is actually highlighting that this behavior is basically due to the correction. Okay, so with this information in our hands about the symbol and about the bounds for the norms, we can give more insight. We can be more precise about the conditioning of our matrices. So we know they are ill-conditioned. Now we can say how much they are ill-conditioned. In case of Riemann-Liouville matrices, we can say that the conditioning is growing as n to the alpha due to the 0 at the origin over the alpha. In case of Kabuto matrices, what we can say is that the conditioning can be greater than n to the alpha and can be up to n divided by 2 plus 1, which means then that at the end of the day, the conditioning for the Kabuto matrices can be worse than that for the Riemann-Liouville ones, especially when alpha tends to 1. And this is due, this we know, to a larger singular value outlier. Okay, so in principle, this ill-conditioning, this worse conditioning of the Kabuto matrices with respect to the Riemann-Liouville ones could be an issue. But actually, if we're talking about the solution of the linear systems associated to these matrices, this is not really an issue, just because conjugate gradient type method will be able to briefly manage with this kind of ill-conditioning. And that's because now we know that this ill-conditioning is due to the larger part of the spectrum. On the other hand, this could be still an issue in the context of time evolution problems, where the presence of large outliers could severely limit the choice of the time step size. And in passing, another thing that I'd like to stress is that since these matrices differ by a rank 2 correction, and in case of just the left-handed and right-handed by a rank 1 correction, we can, using the Sherman-Morrison or the Sherman-Morrison-Woodbury formula, put into connection the inverses. And this could be interesting to know, for instance, when looking at approximate inverse practitioners. Okay, so time for some numerics. First thing we did was to check the goodness, say, of our method. In case of Riemann-Liouville derivatives, that's because the model problem was a space one. So we checked the accuracy in this for the Riemann-Liouville case. What we know from non-fractional diffusion problems is that the approximation order for a B-spline collocation is expected to be P for even P and P minus 1 for P. What we have shown numerically is that for our fractional problem, the order goes P plus 2 minus alpha for even P and P plus 1 minus alpha for odd P. And this is, of course, consistent with the non-fractional. As highlighted here in this table, where the solution is this non-polynomial smooth function here. For instance, for P equal to 4 and alpha equal to 1.2, then the order that we get is 4.8, which is exactly P plus 2 minus 1.2. Okay, final test. Here I'm checking the condition number, the minimum and the maximum singular values of our matrices, both in Riemann-Liouville and Kabuto sets. And then we look also at the ill-conditioning rate of the two to see what I was saying, to check what our theoretical results. Okay, as you see in this table, and as expected, in case of Kabuto matrices, the ill-conditioning, the condition number is always greater than for the Riemann-Liouville case. This especially, as expected again, when alpha is close to 1. And by comparing this column with this one, we can convince ourselves that this is due to the largest singular value. This ill conditioning, this worst conditioning is due to the largest singular value. Okay, final table. Here I'm just showing the conditioning rate for the table in the previous slide. And you see that for Riemann-Liouville matrices, the conditioning rate is just alpha as expected, while for Kabuto matrices, it is always greater than alpha. And actually, it seems to go as alpha divided by 2 plus 1 for alpha close to 1. Okay, so just 2 words on what's next. Well, there is still a lot to do from many perspectives. Concerning the approximation point of view, we'd like to switch to locally non-uniform null sequence to improve the accuracy also for non-smooth solutions. And of course, now that we know all this information on the spectrum of these matrices, we'd like to use this information in order to design ad hoc solvers for instance, for time fractional wave equations. That's it. Thank you for your attention.
Are there any questions from? Are there any questions from the audience?
Apart from Forza Italia.
I think Roberto.
Yes.
Yes, please.
Okay, now maybe I can speak louder because I'm close to the webcam. Do you think that the better conditioning of Riemann-Liouville with respect to Kabuto could depend in some way from the way in which you build the spline basis, in particular for the assumption that you made on the outside of the interval, you consider the just function equal to 0 side, both from Riemann-Liouville and Kabuto. And my question is, do you think it can depend on this part of the spline?
Well, you're right that this is for a specific choice of the boundary conditions, and it's not obvious to see what happens in case we change the boundary conditions. But I would say that I still expect a difference between the two as far as we go for a method that involves basis functions, because we will have always to take into account the derivatives of our basis functions, and I think that that's the part that it's causing this difference. To know if it's actually related to this very specific choice of the boundary conditions, but what I'm expecting is that it would be replicated also for other boundary conditions.
Thank you.
Thanks.
Is there any other question? Maybe from nothing online. So if not, let's thank Myros again.
Thank you.
We go for the let me change. Sorry. Okay. The next speaker is Kabuto, again from University of Insubria, and he will talk us about multi-grid methods for the solution of space fractional diffusion equations. So, then
the first introduction. So, well, I don't need to convince you that fractional derivatives are useful, so I will go straight to the topic. In this work, we study two-dimensional space fractional diffusion equations, where the fractional derivative is in space. We have a standard derivative in time. And the anisotropic case shows up when the diffusion in one direction is stronger than in the other direction. This is the model. We have the fractional derivatives, left and right fractional derivatives in the first spatial dimension of order alpha, the respective diffusion coefficients, time derivative, same thing in the second spatial dimension, and the first interval. Then we have absorbing boundary conditions and solution at the initial time. There are many ways to generate anisotropy. We only consider anisotropies generated by a large difference between fractional derivative orders. And so first we will discretize the fractional diffusion equation. In the case of constant diffusion coefficients, we will obtain a sequence of a linear system. Each linear system will have a topics structure. We will exploit the generating function to have an idea of the spectrum of the topics, and we will use the spectral study and the topics structure to design an efficient multi-fit precondition for generation. We use the Greenwald difference to define the fractional derivative, but we wanted to build a second order scheme, so we had, since the Greenwald difference is a first order approximation, we had to use to introduce the shifted Greenwald difference, which is just the same thing as before with a shifting parameter. And by opportunely averaging the two shifted Greenwald difference with two different shifting parameters, we obtain the weighted and shifted Greenwald difference, which is a second order approximation of the fractional derivative. And the form of the Greenwald difference directly leads to a finite difference scheme. In the matrix representation shows the topics structure, since the operator is a shifting invariant. And the study of the coefficients shows that the decay with an order that depends on the fractional derivative order. Well, Maria Rosa said everything I wanted to say about topics matrices, so we just keep a couple of slides. Well, I just say that the generating function of the topics is needed to build the projector in multigrid. So it will be important to know where the zero is, the position, and the order of the zero. Here is a matrix representation of the left discretized fraction derivative operator. The right one is the same thing as transposed. So the generating function of the sum between the two is the sum between the two matrices is a symmetric. So the symbol is a real function which is non-positive and has a unique zero at x equal to 0 or for the alpha. We use the later. So we have to discretize the diffusion coefficients, which are just function or constant, and the time derivative. And the diffusion coefficients are, yes, diagonal matrices. The discretization of the fractional derivative operator in 2 dimensions is done through the Kronecker product. And the time derivative discretized through the Planck-Nicholson technique. And this leads to a sequence of linear systems that we have to solve. Each linear system has the structure where S and R are the two grid-dependent scale parameter, and they also depend on the fractional derivative orders. So if we suppose that the grid widths are all equal, a large difference between alpha and beta generates a large difference between S and R, and this generates anisotropy. So if we suppose that R is much bigger than S, the diffusion over along the x-axis is stronger than in the other direction. So we have an anisotropy along the y-axis. In terms of symbol, suppose that R and S tends to infinity. In the case where the ratio is constant, we have a symbol that has a unique 0 at x equal to y equal to 0 of order less than 2. When in the anisotropic case, the ratio tends to 0 or infinity, so one of the two variables vanishes. So we have we lose the uniqueness of the 0. We have a symbol that vanishes over an entire line. So let's introduce multi-grid methods. At the basis, we find the two-grid method, which consists in a stationary iterative methods like Jacobi-Gauss-Seidel, and another algorithm which is called the course correction, which is a step 1 to 5. So two-grid consists in computing the residual, projecting the residual over a coarser grid, projecting the matrix over a coarser grid, solving the approximated error equation over the coarser grid, which is less computationally expensive, projecting back the solution over the fine grid, applying the correction. And at the end, we perform a few steps of a splitter. Since our this algorithm is expensive, the solution is computed over the second grid, which should be not so coarse. We can replace step 4 with a recursive call of the grid in order to reach a lower level where the grid is really coarse and the solution is cheap. And this, the resulting algorithm is called the cycle. And since our coefficient matrix is dense, we can replace the projection to through products with other matrices with a rediscretization of the equation over a coarser grid. And this also allows to maintain the structure of the matrix at each level. Okay, so how do we build a projector? Well, here is the formal theorem, but just ignore it. Let's take a look at the end of the slide. We have this is the requirement. We have only in the isotropic case, we have a limit 0 at 0, 0. We need to generate the projector, we need a polynomial which vanishes at the so-called mirror points in red. So by choosing a function p, we have a 0 over the line between the mirror points. So this satisfies the theorem. And it will be enough to build our projectors. These the topics which is generated by this polynomial is a two-level topics. It has a block structure, and the projector are generated by removing a block every 2, and inside the blocks a line every 2. So we have the rectangular matrix representing the projector. The previous one was the projector for the isotropic case, but we have an anisotropic case, and the previous theorem does not hold anymore because the 0 is not unique. In the case of where the symbol vanishes over a line, we have to decrease, well, we consider the function as it does not depend on a variable y. We suppose that the anisotropy is along the y variable. So we consider y as a constant since it vanishes. We forget about it. Then we apply the theorem in the one-dimensional version. So we build the projector as it will be in the one-dimensional case. And the same and almost the same theorem as before applies. So the mirror point would be if the 0 is in position 0, the mirror point would be pi. So the same, almost the same polynomial as before is fine. But we still need the block structure. So the projector is still built in a block structure where each block is a topic with this symbol, and the project since we only project along one of the two variables, we do not remove a block every 2, but only one row every 2 in the blocks. So instead of projecting along the both axes, we only project along one of the 2. This is called the semi-coursing, and it is useful in anisotropic cases. It is a standard method. And what about the smoother? The smoother we use the weighted Jacobi. Weighted Jacobi is standard, but we have to find a suitable weight. The theory states that any weight between 0 and 1 would be suitable, but in real application, a fixed choice of the weight could lead to a slow algorithm. So we have to numerically estimate it. And we came out with this strategy. This is our original linear system. We discretize the linear system over a coarser grid and tilde, while keeping the same scale factor as before. And we compute the iteration matrix of Jacobi. Since the iteration matrix of Jacobi is now smaller, we can compute its spectrum. And this would look like the spectrum of the original iteration matrix of Jacobi, but it is just an approximation. So Jacobi converges whenever the spectral radius is less than 1. So we want the whole spectrum of Bn to be inside the red region, but we only have the spectrum of B tilde. So we use a smaller region to avoid possible outliers to go inside the red region. And we find out, we look for the largest omega weight such that the whole spectrum of the smaller matrix is inside the blue region. And this, if the region, blue region is suitable, would lead to a convergent algorithm even in the original case where the matrix is larger. Here we have a small example. We have a small matrix to the power of 8. here we see its spectrum is inside the blue region. In the original case, the matrix is 64 times bigger, and we see some outliers here and there, but they are still inside the red region, so Jacobi converges. And this actually works even with much bigger matrices. The only problem was my computer wasn't able to compute the spectrum. And okay, this is our proposal. Standard semi-coarse ring seems to be too weak to deal with strong anisotropies. So we found in literature this algorithm, which is a non-standard multigrid of Osterlin in 1995, and consists in a central Bose cycle in black with both coarse ring, with whose pre-smoother, the smoother done before the post-split correction, is a smoother with semi-coarse ring along one direction, and the post-smoother in red is another semi-coarse ring in another direction. So we have both semi-coarse ring, and this was introduced to deal with problems where the anisotropy was along between the coordinate axis. And since in our case the problem is along the coordinate axis, we don't need one of the two smoother. We only keep the one we need. So since it is an expensive algorithm, it is a smoother inside another. It is a multigrid inside another multigrid. We only keep one of the two smoother, the one we need, and perform only one iteration. Then we replace the coefficient matrix with a block band approximation by replacing the fractional derivative operator with a pentadiagonal approximation when the fractional derivative is close to 1, or the Laplacian when the fractional derivative is close to 2. Okay, each iteration of MGS has a linear cost due to the band approximation of the coefficient matrix. So we compare our proposal with its smoother, which was a standard strategy, standard semi-coarse ring, and with other strategies found in literature, like the cycle applied to the two-dimensional Laplacian with weight fixed at 1. Even if you change the weight, it doesn't change anything, almost anything in later tests. And this Bose cycle is a full coursing and semi-coarse ring. Still, Bose cycle with full coursing and semi-coarse ring applied to the original coefficient matrix, and weight fixed to 1, and a standard circular preconditioner. So the equation is this one, where the diffusion coefficient could vanish, they vanish at the edges of the domain. And here we have a table with all our methods, the time, the CPU time, and average iteration per time step, and the size. The size, the amount of grid points is the same over each grid. So the fraction derivatives are 1.5 and 1.1, so the anisotropy is not too strong. But even in this case, where MGS and standard semi-coarse ring are both stable as the size increases, the iteration do not increase. But since MGS is much more robust, the iteration are less, and it allows to spare some CPU time. In this case, all others solvers require more time and more iterations. If we increase the anisotropy from 1.5 to 1.9, the iteration decreases because now the Laplacian is a better approximation to the fractional derivative. And we also show the results when increasing the final time. So we are increasing the time step. This will increase both scale parameter R and S, and the yield conditioning of the system increases. And we see that the only one while anisotropy increases and also the yield condition increases. The only one which is stable as iterations as the sizing increases T is our proposal, which the large computational cost pays back in this case. So, in conclusion, I've shown that suitable weights can be computed with a low computational cost, that MGS is a valid alternative to standard semi-coarsening, and the band approximation allows an easy parallel implementation. And other works would be to a parallel implementation and to apply these strategies to other discretization and parallel time utility solver. We did already something in this direction, but only in the one-dimensional case. And that's it. Thank you for the attention.
Thank you very much, Ken, for the presentation. Yes. Are there any questions from the audience or from Zoom? No. If there are no from here, I found. Was interested. You need
I was interested in the basic model equation, anisotropic diffusion, fractional diffusion. You use the Rees coupled, okay, because you are using discrete version. If you are going in the continuous version, it's the Rees, I suppose. But you can do a divergence form with a sort of fractional gradient. You can, if you want an isotropic version of the fractional diffusion, it means of a sort of fractional gradient. Yesterday I listed something about fractional gradient. Divergence form of the fractional diffusion, and then you can try to discretize. Then just curiosity, because on the formalization of the problem.
Well, I don't know, but thank you. I'm not sure I understand the question, but you mean to change the form of the derivative to use another one? I only dealt with this kind of problem. A change probably would lead to different discretization and everything else, but the same strategy would, of course, apply. And it will require a new study of the spectrum of the matrix. But I tried this strategy with other operators, not the one you are suggesting. And in any case, the yield conditioning was in the same position with the same order. So I think the same strategy would apply in the way I described in this talk.
Okay. Thank you. Are there any other questions? Yeah, just a quick curiosity. How many levels of multi-hierarchy you build?
I had to use as many as I could because the semi-coarsening, the only problem is since I had to reduce only the amount of grid points over one of the two directions, the other one had the same amount of grid points at each level. So I had to go as far as I could till 1 point on the other direction, the one which I could reduce.
Okay, so the smoother is moved down to the minimum size possible. I see.
The central one, I think I stopped it at small matrix, for example, 4 by 4.
4 by 4, independently of the overall size.
Yes.
So it's the number of levels grows as you go up with the size. Okay, so if there are no other questions, I think we can thank again Ken.
Thank you.
Move to the last speaker of this session, that is Pranav. Okay, the last speaker of this session, that is Stefano Massei from
Technische Universität in Leuven. I did the correct pronunciation. And he's going to talk us about rational Krylov method for fractional powers of matrices. So please,
Thank you, Fabio. So in today's talk, I would like to tell you about this joint project with the robot. And so we both got interested into this the problem of approximating the action of a matrix function over a vector. And I hope that the speakers of the morning session and also Professor Salgado yesterday had convinced you that this might be a useful task. Also, when we're speaking about application related to fractional models. And so I can restrict to just the linear algebra here. So what we want to compute is this guy here, where f is the negative fractional power z to the minus alpha, where alpha lies in between 0 and 1. And A is a positive definite matrix. So because we have in mind, for example, to approach some fractional diffusion problem where A is the discretization of the usual Laplace operator, and then you just apply the negative fractional powers and you compute this product to solve your linear system. And the setting we are interested in is when A is rather large, so that again we are not allowed to form this guy explicitly, but we may have some further structure, additional structure, which is so more than positive definiteness. Maybe A is sparse, so that we can cheaply evaluate matrix vector products for solving shifted linear system. And let me just repeat what has already been said. So in this setting, one usually goes for projecting on a subspace. So you generate an orthogonal basis that span a small dimensional subspace. Then you project both the matrix and the vector. You solve your task. That can be either a linear system or in this case a matrix function. And then you project back the solution on the original space by multiplying with it. So this task here is convenient because you have to deal with small matrices and vector. For example, in this setting, you can do it with directly by diagonalization because this is still an Hermitian matrix, so you can do this operation safely. And the quality of this approximation, of course, strongly depends on how you choose the subspace spanned by U. And the popular choices are Krylov subspaces, because in this case you can link the convergence as your space become larger and larger to the solution of a polynomial approximation problem, for example, of the function f over the spectrum of your matrix. And so in particular, you have this quasi-optimality result, that the error is bounded by the 2 times the best polynomial approximation of your function. But of course, for us, polynomials are not good because we have a singularity in 0, and probably you have some eigenvalues close to 0, so you have to move into the direction of rational functions. And that's why you consider the rational version of the Krylov subspace that has been already introduced and is defined like with this expression. And in particular, you have to choose a set of parameters that will represent the poles of your rational approximation. So in the end, once you have made this choice, you end up with the bound for the error that is given with respect to the best rational approximation of your function, where the poles of the rational approximant are exactly these parameters here. So in particular, the questions that we wanted to address with this project are, how should I choose these parameters here? And what can I say about an explicit bound for this? So something that is not related to a rational approximation problem. And actually, we address this problem in a wider class with respect to the negative fractional powers. We consider the Cauchy tiltages class or Markov function class. So in particular, all functions that can be represented as a convolution of the Cauchy kernel, 1 over z plus t, with a negative measure on the positive semi-axis. And in particular, we do not care about this mu in this talk. So mu can be whatever, and because it is an approach that holds for a general element in this class. And yeah, just to wrap up, so what we want to do is to do this, compute this guy via rational Krylov, and we want to a strategy for selecting the poles and explicit estimates on this. So let me sketch the idea. So if you write exploiting the integral representation of the function, what you're going to compute, you have this on the left-hand side. And on the right-hand side, you may write what is the projected quantity that you're computing. So you see that by linearity, you can move the u here inside the integral. And this should shed some light on what is the property that you're looking for you. So in particular, if you look, this integral is a good approximation of this integral if the integrand is well approximated. So you need to approximate all these resolvent as t varies uniformly well in your space. So this is basically the property you are looking for. And this is not super trivial because when you look for a rational Krylov space, if you generate the space with A or A plus di, then you end up with a different space. So it is not super trivial to understand what is happening here once you made a precise choice of your poles. And so the idea is to try to approximate directly this Bavarian function, the Cauchy kernel, on the following infinite strip. So you have the Cartesian product of the set of the interval where the eigenvalue live times the semi-axis 0 infinity, which is where the parameter t varies. And the point is that this specific function here admits a very special rational approximation. And the challenge was to show that this approximation of the Cauchy kernel is contained into the rational Krylov space we are generating. And so the approximation I'm talking about is called the skeleton approximation, and it is an interpolation over a grid. So you take some points here, the lambda I, you take some points there, the tj, and then you impose that your approximation match the Cauchy kernel on the grid given by the pairs lambda I tj. And so this rational function can be expressed with a matrix vector notation like this. And more importantly, has two important properties. So the first one is that you have an explicit expression for the error. So in particular, the relative error is given by the ratio of the same rational function once evaluated in lambda and once evaluated in minus t. And the second one is that if you look at this guy here as a function of lambda, so imagine that t is fixed. So this thing is a rational function whose poles are exactly the parameters tj's. So the idea is that if you generate the Krylov space choosing as this at sigma the parameters minus tj, then your space contains the skeleton approximation, and then you can use this formula for deriving an upper bound for the error. And if you go in this direction, you can first find a pointwise bound for the error you made once you approximate the resolvent for a generic t. And you have that the error is bounded by the product of two terms, the first one that still depends on t, and the second one which does not depend on t, but is given in terms of the solution, the optimal value of a rational approximation problem. And where you still have the degrees of freedom of choosing the poles of this rational function. So if you take a look more closely, you want to find a rational function that is, so you want to make this term the smallest as possible, right? Because this is the error. So you want a rational function that is the smallest as possible on the set of the eigenvalues, and which is the biggest as possible on the negative semi-axis. So you can play a bit around with this problem. You can symmetrize it because you can prove that this is invariant Untitled transformation. So you can map the semi-axis and the interval into AB and the mirrored interval minus B minus A. Maybe you can say this is not a big improvement because I still don't know how to solve this problem, but luckily there is someone that already did it for us, actually quite some time ago, because this problem was solved by Zolotarev, who was a student of Chebyshev in the 19th century, and it actually also posed the problem and solved it, so it did everything by itself. So it shows that so the optimal rational function for this problem has an explicit expression. So we have a closed formula for its poles, and we also have estimates for what is the optimal value of this problem. So the idea is to take the Zolotarev solution here and map its poles back with the inverse Mobius transformation, so that we get our original rational approximation problem. And if you do that, you end up with this upper bound for the error after L steps of the rational parallel subspace. So you have an exponential decay in the error that depends mildly on the condition number of the matrix. So it appears just at the denominator of the exponent inside the logarithm. And you have an explicit computable quantity here. Maybe you have f of lambda mean that plays a bit the role of a condition number in the constant. And so we give it a try, and so we try this choice of poles, and we compare with some usual choice for the Krylov subspaces. So we have, for example, polynomial Krylov that we know do not converge at all. Then we have standard Krylov where we just alternating 0 and infinity as poles. And then we have what we think is the state-of-the-art method for this kind of problem. So it is a greedy strategy for choosing the poles while creating your rational parallel subspace. And you see that it seems to outperform, at least for this problem. And we also try with increasing dimension. We think that the gap, at least for the first iteration, it becomes more evident. And then we move to a special particular case of evaluating the action of the matrix function times a vector, motivated by problems in 2D. So, for example, when we are in 2 dimension and we are using tensor grid for discretizing your problem, you might end up with a structure like this for the matrix. You might have a Kronecker sum, and then also the right-hand side, which might be the discretization of a source stem that is moved on a square, for example, or something that has a small support. Then it might be the vectorization of a Lorac matrix. So we want to do the same, evaluating f of a matrix times a vector, but this time the matrix has this Kronecker sum structure, and the vector is the vectorization of a Lorac matrix. And still we assume that the Kronecker sum is positive definite. And this was kind of interesting because coming from linear algebra, we know that when the function is set to the -1, well, this problem corresponds to solving a Sylvester equation, which is an important problem in control theory. And there is known that whenever you have that C is low rank, then this property is also verified on the solution, at least numerically. So you also have the solution of this matrix equation is numerically low rank. So a natural question is this true when we replace z to the -1 with z to the -alpha? And the answer is yes. And we can provide a rigorous argument for this using the error analysis for the rational parallel subspace. So again, in this setting, the point is to project on a subspace, but this time we also choose a Kronecker form for for the space project. Because if you do this choice, so if you generate, for example, if you are in dimension n squared, you generate two spaces of dimension n, and then you have two bases, u and v, and then you choose all the vectors that are given by the Kronecker product of u and v. And why we do that? Because if you project using an orthogonal basis of this form, then you retain the Kronecker sum structure also on the projected matrices and vector, and you can still come up with a method for solving the projected problem that has a cubic complexity with respect to the dimension of these spaces that is small. So in the interest of time, I can just sketch a little bit how to modify the idea for addressing the 2D version of the problem. So if you write down the integral expression of what you are computing, you are this time in place of resolvent, you are integrating the solution of a parameter-dependent Sylvester equation, where the parameter affects. You might make the parameter T2 only change one of the two coefficients, for example. And again, you can relate the convergence of your. You basically want to generate a rational Carl subspace that is good for projecting all equations of this form for as t varies. And again, you can connect this task to solving a Zolotarev problem. You just slightly change what are the two sets here. So again, you can symmetrize it and take the solution by Zolotarev and maps the fallback. And you can prove an analogous statement, so where you have a similar exponent, and your constant deteriorates slightly. You have an additional condition number here in the constant. But basically, you have a decay rate that is kind of optimal because if you compare it with the case of Sylvester equation, you just have a factor 8 here in place of a factor 4. And we know that in the case of matrix equation, this is optimal. And so since what you are basically computing after, let's say, L steps of the rational Krylov method is a solution of rank L times the initial rank of your right-hand side. You can use this bound together with a Neckart-Young argument to say that this is also a bound for a certain singular value. So you can say that this guy here, which is the bound from the theorem, is also bound for the singular values of x, and you see that is able to capture the decay in the singular values of the quantity you are computing. So let me conclude by saying that there is a bit of a catch in these polls by Zolotarev, which is the fact that they are not tested. So if you want the poles of the optimal rational function of degree L and the one of degree L plus 1, then these two sets of poles are not do not share anything. So in theory, you should recreate your Krylov subspace from scratch, which is really a big drawback for the computational side. But there is a nice workaround due to the fact that so these poles at infinity, they generate a well-known measure on the interval AB. So one can directly generate sampling from this measure and generate a nested sequence of poles, and for which you can augment the Krylov subspace in the usual manner. And one can experience a very similar convergence rate as the one of the optimal poles. And I think that's it on my side. So thank you for your attention.
Very much, Stefano, for the talk. Are there any questions from the room of Zoom? Okay, I have actually one. So to solve the problem, you have to solve the inner matrix equation. So if it
you are saying about the projected problem. Kind of. You still have to compute a function of Kronecker sum.
Okay.
But again, since you're projecting with this very nice structure of the basis, you still have a Kronecker sum for the projection, and you can directly diagonalize, so the A and B, because they are still Hermitian. And then you have here a diagonal matrix, so you can actually write down this as another mark product of the matrix that has the evaluation of the function on all the possible pairs of eigenvalues times this matrix here. Then do the projection back with this.
Okay. Are there any other curiosities, questions, comments? Doesn't seem so. So let's thank Stefan again. The speakers of this session, and I think we can go for the coffee break. And then we are back in half an hour. Yes.
Stato sulla
you.